Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay. 1995 Michel Mayor. Didier Queloz, a Jupiter mass companioned with solar-type star. The announcement, in 1995, of a Jupiter mass planet orbiting a Sun-like star, 51 Pegasi, represented a seismic shift in our understanding of planetary systems. The work of Michel Mayor and Didier Queloz, published in Nature, presented compelling evidence for an object whose orbital period, approximately 4.2 days, defied conventional models predicting long-period orbits for gas giants. This essay will embark on a section-by-section examination of this groundbreaking paper, meticulously evaluating the claims the authors presented, the methodologies they employed, and the implications of their findings, all while adhering to the constraints of this exercise. We will eschew repetition and dichotomy, focusing instead on a rigorous and direct assessment of the paper's internal logic and its lasting contribution to astronomical science. Section 1: Introduction, Radial Velocity Measurements and Planet Detection. The introductory section of Mayor and Queloz's paper establishes the framework for their investigation. They introduce the technique of radial velocity measurements, a method based on the Doppler effect, to detect the subtle wobble of a star caused by the gravitational pull of an orbiting planet. This section lays the groundwork by explaining how a planet's existence manifests in the observed spectrum of its host star. The authors correctly state that the shift in spectral lines, blue shift when the star is approaching, red shift when it is receding, offers a pathway to ascertain the radial velocity and, consequently, deduce the presence of an orbiting. The core claim presented here, that radial velocity measurements are a valid technique for detecting planets, is grounded in established physics. The authors provide a brief, clear explanation of the underlying physics, the Doppler effect, the critical aspect of this section, and subsequently the entire paper rests on the precision of the measurements. The ability to detect a Jupiter mass planet requires extraordinarily accurate measurements, demanding the capability to discern variations in stellar velocity on the order of meters per second. It is a challenge they suggest their instrument, the Elodie spectrograph, is designed to meet. This initial premise is central to the paper's success. The accuracy of their measurements would serve as the foundation for their revolutionary conclusion. Section 2: Observations of 51 Pegasi. The discovery. The heart of the paper resides in the presentation of the data and the subsequent analysis. The authors focus on the observations of 51 Pegasi, a solar-type star previously studied for its spectroscopic properties. This section begins with a description of the data acquisition. The data was obtained using the Elodie spectrograph at the Observatoire de Haute Rephrase. They detail the dates, times, and exposure durations. Significantly, the authors mention the calibration procedures implemented to ensure the accuracy of their measurements. These procedures are essential for minimizing instrumental errors and systematic biases. The core claim arising from this section is the detection of a periodic variation, a sinusoidal fluctuation, in the radial velocity of 51 Pegasi. They provide a graph illustrating the variation of the radial velocity with time. The data presented in the graph exhibits a clear periodicity, with a period of approximately 4.2 days. The amplitude of the velocity variation, at around 56 meters per second, is substantial. The authors meticulously analyze this data, demonstrating the robustness of this periodic signal. The meticulous presentation of data, accompanied by statistical analysis, provides robust support for the central claim's validity. The authors do not initially present an interpretation, they present the data as the starting point for deriving the scientific impact. Section 3: Orbital Parameters and Planetary Implications. This section moves to the interpretation of the radial velocity variations. The authors describe how they determined the orbital parameters. The periodicity is the most immediate finding. The swift orbital period, a mere 4.2 days, presents the primary challenge to prevailing theories of planetary formation. The conventional accretion models of that era suggested gas giants formed at considerable distances from their stars, where temperatures are sufficiently low for the condensation of volatile compounds. The close proximity of the companion to 51 Pegasi required a radical revision of these models. The authors deduce the minimum mass for the companion by applying established orbital equations. They use the amplitude of the radial velocity variations and the assumed stellar mass. The deduced minimum mass of the companion is close to that of Jupiter. The authors acknowledge that this value represents a minimum. They explain how the orientation of the orbit relative to the observer introduces an uncertainty, meaning the true mass is potentially larger, even if the orbit were inclined. The authors correctly assert the companion would still be substantial, making the implications important. The authors also examine the possibility of additional companions, finding evidence for only one. They consider the possibility of a second planet, but the data does not support it, allowing them to present their conclusion with a high degree of confidence. Section 4. Discussion and implications. The final section of the paper is dedicated to the implications of their findings and their significance. The authors directly confront the unexpected orbital characteristics of the discovered planet. They recognized their discovery challenged the standard model of planetary formation, specifically the paradigm that gas giants would form far from the central star. They consider several potential explanations. One possibility they consider is the planetary migration scenario. They entertain the idea that the planet formed further away from 51 Pegasi and subsequently moved towards the star. This mechanism allows the planet to be positioned much closer to its star than had previously been thought possible. The authors correctly stress that the planetary migration scenario is a radical departure from established thinking. They also mention that the planet's proximity to the star should lead to atmospheric effects, such as extremely high temperatures. They suggest atmospheric characterization as a future avenue of exploration. The authors close with a summary of their findings, emphasizing the necessity of revision to established planetary formation models and stressing the importance of continued research. Conclusion. Assessing enduring legacy. The work of Mayor and Queloz, as presented in a Jupiter mass companion to a solar-type star, represents an epochal achievement. The paper's core strength emanates from its meticulous attention to detail, its rigorous methodology, and its cautious approach to interpreting the data. Each section of the paper, from the introduction of the radial velocity technique to the discussion of implications, is logically structured. The claims are clearly stated. The evidence is presented with meticulous care. The arguments are logically constructed. The conclusions are presented with appropriate caution, acknowledging the scope of the findings. The paper, without directly stating it, implicitly challenges the prevailing models of planetary formation, ushering in a new era of exoplanet research. The paper's impact is twofold. Firstly, it presents a paradigm shift. The discovery of 51 Pegasi b forced the astronomical community to reconsider the processes by which planets form and evolve. The confirmation of a hot Jupiter, a gas giant orbiting extremely close to its star, spurred revisions to existing models. Planetary migration, once a theoretical possibility, became a critical component of planetary formation theories. The recognition that planets, once formed, are still in a state of evolution, with the potential to move, contributed a new dimension to the study of planetary systems. Secondly, the paper established the foundation for numerous subsequent discoveries. The success of the team's approach served as a proof of concept, demonstrating the efficacy of high-precision radial velocity measurements. This technique subsequently spearheaded the discovery of hundreds, if not more, of exoplanets in the following decades. The Elodie spectrograph, and the data it generated, served as a template that inspired the design and construction of more advanced instruments. The legacy of 51 Pegasi b is now embodied by a generation of instruments that continuously expand its impact. The careful methodology and precise results outlined in this paper enabled the exoplanet revolution. The paper's lasting influence remains evident in the ongoing study of exoplanets. Subsequent observations have verified the existence of 51 Pegasi b and characterized its atmosphere. Further researchers continue exploring the details of its orbit and its interactions with its host star. The study also catalyzed the development of new techniques that have expanded on the original methodology. For example, the method of transit photometry, enabled by the precise radial velocity measurements, has provided a useful cross-check. Other techniques allow the study of exoplanets in more detail, including the collection of spectra and direct imaging. The 1995 paper stands as a testament to the power of observation, the value of careful measurement, and the capacity of scientific inquiry to overturn established paradigms. The meticulous approach to data acquisition, the clear presentation of results, and the cautious interpretation of implications combined to establish a turning point in the history of astronomy, one that continues to inspire exploration and understanding of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.